My name is Fouad Khelifi. I am the module tutor for machine learning and computer vision module. First of all, sorry for the last minute change of the room. So still trying to resolve that with the timetabling team. So the module will be delivered over 24 weeks, so it will be year-long module for the first time, and there will be two tutors delivering the module. So I will be doing the first semester. The first part will be on machine learning. The second part will be covered by Martin in semester 2. This is a 20 credit module, 23 weeks of alternating lectures and labs. There will be a guest lecture given at the end. Obviously, lectures and are structured and linked. You will see, so we will start from the very beginning, try to understand what is machine learning, what is linear classification, the basic linear classification system using the gradient descent, and then we will gradually learn some more sophisticated classifiers, machine learning techniques, and computer vision systems. So it's gradual. Your attendance is essential. Please, if you miss a lecture, if you can't understand some material, do contact me as soon as you can. It is important that you understand all the material, so that you can basically progress over the 24 weeks period. There will be 2 hour lab sessions held fortnightly every 2 weeks. So alternating with lectures, so 2 hours lecture and then 2 hours lab in the following week. 1 assignment, individual assignments. So it will be released on the 24th of January 2019. It will be a Thursday. And submission deadline will be on the 9th of May 2019. So you will have, by then you will have seen enough material through lectures and lab sessions, so you'll be able to start working on the assignments in semester 1. So you'll have at least completed the first part of machine learning. You will have seen enough machine learning techniques and classifiers. Learning outcomes of the module. First is to so students at the end of the module or the course will be able to demonstrate knowledge and understanding of the theory and practice of modern digital techniques for the capture, processing and storage of visual data. Critically analyze legal and ethical issues in computer vision, as well as current technologies for security. Apply and critically evaluate appropriate machine learning techniques to solve problems in computer vision. So basically, the assignments will rely heavily on the work done during lab sessions and knowledge given in lectures. So basically, students will develop, investigate and critically analyze systems that solve machine learning and computer vision problems. We will use MATLAB as the core programming language in this module. Students are encouraged to undertake the programming part in their own time, but there will be in the very first seminar or lab, there will be a short presentation on MATLAB just an introduction to see the structure of MATLAB programming. It's basically it's a lot easier than other low-level programming languages such as C++ and Java. It's easy to learn. Obviously, examples will be provided in lab sessions. Complete programs in MATLAB, well documented with comments, explanatory comments. So it will be a lot of support in terms of MATLAB programming. So this is the structure of the module. So that's the content. So it will be first part, semester 1. Basically, it's all about machine learning stuff, except the last one. So that will be an introduction to computer vision, image and video representation. In the second part, it will be more focused on the computer vision part. So digital image transforms, wavelets, BCT, Fourier transform, different applications such as image filtering, image enhancement, computer vision security applications such as digital watermarking, perceptual hashing. There will be another application of deep learning for computer vision applications. Basically, you will see the convolutional neural network, which is the latest state of the art in deep learning, which applies directly to digital images and videos. Another application of face recognition using machine learning techniques, and concrete implementation of CNNs in MATLAB. The reading list is available on Blackboard, so there will be some relevant textbooks and online sources. So please do consult the list of resources that is available on Blackboard. Now, just brief introduction about machine learning. So as the name suggests, machine learning studies the design and analysis of computer programs. We also refer to them as systems, automated systems, capable of learning from past experience in order to interpret the data seen or predict, decide in new situations. So basically, it's to mimic the human intelligence. So suppose you've seen a person from distance today, and you will be asked to recognize them in 2 weeks' time. So 2 weeks' time you will recognize them. So what is the probability that the recognition is 100% accurate? So now, what if you see this person twice, today and tomorrow, and then you'll be asked to recognize them in 2 weeks' time? So obviously the accuracy, the recognition accuracy will increase based on the number of times you've seen this person. So it's exactly the same process that happens with automated systems, machine learning systems. So basically we provide a lot of training samples. We call them training samples. So in the case of face recognition, training face images of the same individuals many times, and then the system learns. Because when you see a person first time, perhaps the person is wearing a hat. Second time, the same individual maybe is wearing glasses. And you're still learning. It's a learning process. Next time, maybe the person is, you will see them in 2 weeks' time with the beard, and you will be able to recognize them based on past experience, because you have seen them many times with different patterns. Sometimes wearing a hat, sometimes shaving, sometimes maybe with glasses. So these different patterns of the same instance, the same individual, will allow you to learn the intra-class variation. So it's the same individual, but there will be some slight variations. So it's exactly the same process that happens to automated systems. So automated systems, machine learning systems, require a lot of training samples in order to learn the variation within the same class. So here is an interesting maybe introduction to machine learning. It's just 10 minutes long. Just watch the video and then we'll come back to the material.
Hello there, my name is Gary Sims from Android Authority. Now, one area of computing that is improving the way we use our smartphones and use the web is machine learning. Now, sometimes machine learning and AI get used interchangeably, especially by big brand companies that want to announce their latest innovations. However, machine learning and AI are quite two distinct areas of computing. However, of course, they are connected. And today we're going to ask ourselves the question, what is machine learning? The goal of AI is to create a machine that can mimic a human mind. And to do that, of course, it needs learning capabilities. However, it's more than just about learning. It's also about knowledge representation, reasoning, and even things like abstract thinking. Machine learning, on the other hand, is solely focused on writing software that can learn from past experience. One thing you might find quite astounding is that in fact machine learning is more closely related to data mining and statistics than it is to AI. Well, why is that? Well, first of all, we need to look at what we mean by machine learning. One of the standard definitions of machine learning, as given by Tom Mitchell, a professor at Carnegie Mellon University, is this: a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at tasks in T, as measured by P, improves with experience E. Okay, well, let me try to put that more simply for you. If a computer program can improve how it performs a certain task based on past experience, then you can say it has learned. This is quite different to a program which can perform a task because its programmers have already defined all the parameters and data needed to perform that task. For example, a computer program can play tic-tac-toe, maybe you call it noughts and crosses, because a programmer wrote the code with a built-in winning strategy. However, a program that has no predefined strategy and only a set of rules about the legal moves will need to learn by repeatedly playing the game until it is able to win. This doesn't only apply to games, it is also true of programs which perform classification and prediction. Classification is the process whereby a machine can recognize and categorize things from a data set, including from visual data and measurement data. Prediction, known as regression in statistics, is where a machine can predict the value of something based on previous values. For example, given a set of characteristics about a house, how much is it worth based on previous house sales? And this leads us to another definition of machine learning. It is the extraction of knowledge from data. You have a question you are trying to answer, and you think the answer is in the data. That is why machine learning is related to statistical analysis and data mining. Machine learning can be split into three categories: supervised learning, unsupervised learning, and reinforcement learning. Let's have a look at what they mean. Supervised learning is where you train the machine using data which is well labelled. That means that the data is already tagged with the correct answer, the correct outcome. Here is a picture of the letter A. This is a flag for the United Kingdom. It has 3 colours. One of them is red, and so on. The greater the data set, the more the machine can learn about the subject matter. After the machine is trained, it's given new, previously unseen data, and the learning algorithm then uses the past experience to give you an outcome. This is the letter A. That is the UK flag, and so on. Unsupervised learning is where the machine is trained using a data set that doesn't have any labels. The learning algorithm is never told what the data represents. Here is a letter, but no other information about which letter it is. Here are the characteristics of a particular flag without naming that flag. Unsupervised learning is like listening to a podcast in a foreign language which you don't understand. You don't have a dictionary and you don't have a supervisor or teacher to tell you what you are listening to. If you listen to just one podcast, it won't be much benefit to you. But if you listen to hundreds of hours of those podcasts, your brain will start to form a model about how a language works. You will start to recognise patterns, and you will start to expect certain sounds. When you do get hold of a dictionary or a tutor, then you will learn that language much quicker. Reinforcement learning is similar to unsupervised learning in that the training data is unlabelled. However, when asked a question about the data, the outcome will be graded. A good example of this is playing games. If the machine wins a game, then the result is trickled back down through the set of moves to reinforce the validity of those moves. This isn't much use if the computer plays just 1 or 2 games, but if it plays thousands, even millions of games, then the cumulative effect of the reinforcement will create a winning strategy. There are many different techniques for building machine learning systems, and many of these techniques are related to data mining and to statistics. For example, if I have a data set which describes different types of coins based on their weight and based on their diameter, I am able to use a technique known as nearest neighbour to help classify previously unseen coins. With nearest neighbour, the new coin is compared to the nearest neighbours around it and see what classification they have. It's then given the same classification as its nearest neighbours. Now you can pick how many neighbours you want to compare against, and that number is often referred to as K. So therefore the full title for this algorithm is K nearest neighbours. However, there are lots of other algorithms that try to do the same thing, but using different methods. Take a look at this diagram. The picture on the top left is the data set. The data is classified into 2 categories, red and blue. Data is hypothetical, however it could represent almost anything. Coin weights and their diameters, the number of petals on a plant and their width. Clearly there are some definite groupings here. Everything in the upper left belongs to the red category and the bottom right is blue. However, in the middle there is some crossover. If you get a new, previously unseen sample which fits somewhere in the middle, does it belong to the red category or the blue category? The other images show different algorithms and how they attempt to categorize a new sample. If the new sample lands in a white area, then it means it can't be classified using that method. The number on the lower right shows the classification accuracy. One of the buzzwords that we hear from companies like Google and Facebook is neural net. A neural net is a machine learning technique modelled on the way neurons work in the human brain. The idea is that given a number of inputs, the neuron will propagate a signal depending on how it interprets those inputs. In machine learning terms, it is done by matrix multiplication along with an activation function. The use of neural networks has increased significantly in recent years, and the current trend is to use deep neural networks with several layers of interconnected neurons. During Google I/O 2015, during the keynote, it was explained how much machine learning and deep neural networks are helping Google fulfill its core mission to organize the world's information and make it universally accessible and useful. To that end, you can ask Google now things like, how do you say Kermit the Frog in Spanish? And because of neural networks, Google is able to do voice recognition, natural language processing, and translation. Currently, Google is using 30-layer neural nets, which is quite impressive. As a result of using these neural networks, Google's error rate for speech recognition has dropped from 23% in 2013 to just 8% in 2015. So we know that companies like Google and Facebook use machine learning to help improve their services. So what can be achieved with machine learning? One interesting area is picture annotation. Here the machine is presented with a photograph and asked to describe it. Here are some examples of machine-generated annotations. The first 2 are quite accurate, although I'm not sure there's a sink in that first picture. And the third is interesting in that the computer managed to detect the box of donuts, but it misinterpreted the other pastries as a cup of coffee.
What is it? It's a banana. No, it isn't. Try again. What is it? It's a banana? No, it isn't. What is it? Come on, say it. It's an orange. This is an orange.
Of course, the algorithms can also get it completely wrong. Look at this first picture. Those men in hard hats seem to be doing some work. However, the computer thinks they're lounging around in a couch. And that motor scooter doesn't look like a fire hydrant to me. And I don't think that horse will be very happy as being described as a surfboard.
What is it? It's a small off-duty Czechoslovakian traffic warden.
Another example is teaching machines how to write. Cleveland Amori, an American author, reporter and commentator, once wrote, "In my days the schools taught two things, love of country and penmanship. Now they don't teach either." I wonder what he would think about this. The above handwriting sample was produced by a recurrent neural network. To train the machine, its creators asked 221 different writers to use a smart whiteboard and copy out some text. During the writing, the position of their pens was tracked using infrared. This resulted in a set of X and Y coordinates which were used for supervised training. As you can see from the results, they're quite impressive. In fact, the machine can actually write in several different styles and at different levels of untidiness. Google recently published a paper about using neural networks as a way to model conversations. As part of the experiment, the researchers trained the machine using 62 million sentences from movie subtitles. As you can imagine, the results are quite interesting. At one point, the machine declares that it's not ashamed of being a philosopher, while later, when asked about discussing morality and ethics, it said, "And how I'm not in the mood for a philosophical debate." So it seems, if you feed a machine a steady diet of Hollywood movie scripts, you get a moody philosopher. Unlike many areas of AI research, machine learning isn't an intangible target. It is a reality that is already working to improve the services we use. In many ways, it is the unsung hero, the uncelebrated star which works in the background, trawling through all our data to try to find the answers we are looking for. And like deep thought from Douglas Adams' Hitchhiker's Guide to the Galaxy, sometimes it is the question we need to understand first before we can understand the answer. My name is Gary Sims from Android Authority, and I hope you've enjoyed this video. If you did, please do give it a thumb.
So, machine learning can be supervised or unsupervised learning. Basically, in supervised learning, so we have labeled data. Basically, the system in the training sample, we know the input data and the target output data. So we have pairs of input and output samples that will be used to train the system. So the training sets, in this case, consist of pairs of samples, input samples, and designed or target output samples. Obviously, in supervised learning, we have two applications in regression and classification. We will see the difference in the later slide. Unsupervised learning is also called clustering. So we have only distribution, some samples. We don't know basically the where these samples belong to. We don't know the classes, the patterns, so the system automatically uses a self-adaptive process to learn from data, and then automatically will decide on the distribution and the classes and the label of every single sample. So this is called clustering. It's probably the most widely known application of clustering is in image segmentation. So you provide the system with an image, perhaps a medical image, which contains some different patterns, tissues and objects. The system automatically will separate or segment the image into different patterns. So this is called image segmentation. And also blind signal separation is another application of clustering, where the system, where we have a number of recorders, but the signals acquired contain multiple speeches at the same time, so people speaking simultaneously. So we've got a number of recordings, so recording systems. So we have a number of signals, but these signals are just a mixture of different speeches. So people speaking obviously different voices. So automatically the system will separate these signals using a clustering technique. So this is called blind signal separation. We don't know the target output. We know for sure the signals are just a mixture of speech patterns, but the system will automatically separate them. Now in supervised learning we have again two classes, regression and classification. So we have machine learning, so that's the broad area. So machine learning could be supervised or unsupervised. So unsupervised, we have clustering. It's also called clustering techniques. So in this module we will see an example of a clustering technique. So that's the k-means clustering technique. In supervised learning, so we have classification, and regression. So in classification, the system predicts categorical class labels. So we'll be talking about classifiers. For example, a system that classifies emails into spams and non-spams. So you can see the output is a category, so a class label. So the output of the system is not a number, is not a continuous value, is not a real number, is not prediction, is not an estimation, is not a quantity, is not something that can be quantified, it's just a category. So if the system predicts class label, so we'll be talking about classification. It's a classification system. Now, if the system produces real number values or integer values, like an estimation, predicts values, quantities, for example, we can train a system to predict a number of students on this module next year. Okay? We can also use some training data, some records, to train the system to predict the number of students who will get a mark higher than 60% this year. So from past experience, from previous years, we can train a model to predict a number. So if the output of the system is a number, integer number, could be a real number, so here it is a regression system. Again, it requires machine learning. It is a learning system, but the difference is here regression, and in the first class is classification. So classification, for instance, detecting a disease, you provide an image to a system, medical system, an image, cells or tissues, and then the system will predict whether the organ is normal or abnormal. So detecting disease is also a class label, is classification problem. Now, input data could be continuous variables or categorical variables. So we will see some examples. Again, so input data, we can measure some input data, we can provide numbers, but also we can provide some description about input data. So again, even if we have some categorical variables, we can quantify them in order to feed the machine learning system. So here we have an example, a linear regression system. So we have, for instance, we have some records. So from past experience, we know, for example, when the house or apartments, the living area is about 100 meters, number of bedrooms is 2, so the price is, for example, is 80,000. Obviously, it depends on the location. That's just an example. So we know from past experience, from our records, these samples. So we've got input data and we know the output, how the price should look like. Okay, so we have some patterns. We can use this data to train a system, and then once the system is trained, we can provide any number for the living area and bedrooms, and the system will predict, will estimate the price. Okay, so this is a problem of this is a regression problem. Now, why it's called linear? So here we have again, so regression or classification. It could be linear or non-linear. So linear means the relationship between output samples and input samples are assumed to be linear or following a linear equation. So when we see the rule, for example, if we have output of the system, so we have some input data, x1, x2, x3, for instance, three features. So the output is y. So if we assume the system is linear, this means the relationship between y and x is linear. So we have a coefficient a x1 plus b x2 plus c x3 plus d. So that's a linear equation. Okay, if we have a square here, x to power of 3, so this is not a linear equation. So linear means it's following the equation of a straight line. Okay, so the equation of a straight line, y equals ax plus b. So suppose we have only one input, so that's the equation of a straight line. Okay, the equation of a curve is ax to the power of 2 plus b. So that's a curve. If you display x and y, so it will be a curve if it's square. Now if it is ax plus b, it will always be straight line. Now depending on a and b. Okay, so that's the so this is a linear equation. So linear regression means the relationship between the output of our system and input samples is linear. So now we have two features. So living area, obviously the problem depends, so the price depends on two features, supposedly depends on two features. So living area and number of bedrooms. Now we have some repeated samples. Well, we have multiple samples, so we have the first sample, second sample, so each sample is just a record, multiple records, because these records have different patterns. We need to use multiple samples for the system to learn. If you use only one single sample, it is difficult for the system to predict in future. When we present new situation, it's difficult to learn from a single sample. So that's why we have multiple samples. So recall the example of face recognition. If you see a person from a distance just once, it will be difficult to recognize them in a month's time. But if you see them twice, even if the person is maybe changing the look, your system is learning, so your brain is learning different patterns within the same individual. So that's exactly the same problem, the same process here. We use multiple samples so that the system will be able to learn from different patterns. Okay, so we have two features, x1 and x2. So x1 is the living area. For example, the first one is 100, 135, 180, and so on. So this is a feature, and this is the second feature. So the feature vector, obviously we can group them in a vector. So we will have feature 1 and feature 2. So two features, it means this is a two-dimensional system. So we'll be talking about a two-dimensional system because we have only two features. So that's the first feature vector, obviously the first sample, and this is the second sample. So we can group the features together. So for each sample we have two features. So we have x1, 1. So that's the first sample of x1, and x2, 1. So that's the definition, just for notation, which is equal to 2, is the first sample of x2. So we have multiple samples and only two features. Obviously, the target desired output is the price recorded from past experience. Now, if we assume the system is linear, so the output y equals, so this is another parameter, theta 0 plus theta 1 x1 plus theta 2 x2, and so on. So the objective is to update the parameters of the system. So we have, in this case, we have three parameters. By using the training set, obviously training set is a pair of samples, so the feature vector and the target output. So the most basic learning rule or training rule is called the gradient descent algorithm, and this is the core learning rule of the artificial neural networks. So this is, we have a very simple example here, a simple problem, but in the most complicated structure of artificial neural networks, we also use the gradient descent method. So the gradient descent method is obviously used to update the parameters of the system. So the idea of updating the parameters of the system is that we initially start by initializing any random numbers for these parameters, but then these parameters will be updated using the different samples. Okay, so you can see here we have the target output and the output of the system. Now the difference will be like a regression error that will be used to update the parameters. So we are using obviously the same rule for every single parameters. So alpha is a constant, is called the learning rate. Obviously it has to be much smaller than 1. This is the case of 2 features. So we have 2 features, it means 3 parameters, so theta 0, theta 1 and theta 2. But in general, if the system is has n features, so that's the common rule used to update the parameters using the gradient descent method. So it is an iterative process. Obviously, the first step is to initialize it with random parameters, so theta 0, theta 1 and theta 2, random values. Now the second step is to update the parameters based on the output of the system. So we will calculate the output of the system using the initialized parameters. So obviously we will see some differences. Using these differences, we will update the initial parameters, and then we keep updating the initial parameters until we get maybe the classification error smaller than a certain threshold. Obviously the threshold will be set by the user. So that's the learning process. So the idea here is to start with any random numbers and then measure the output of the system. So we have the target output, we have the desired output, and then we do the difference. So we measure the output of the system using any random parameters. So using the difference, we will update the parameters of the system in an iterative way. So that's how it works. Obviously, we will see the implementation of this system next week in the lab. So in MATLAB, it will be implemented, and you will see this, the implementation of this rule. So we have an example here. For example, we can initialize the system randomly. Theta 0 equals -4. Theta 1, 3, theta 2 is 2, theta 2 is 6. Now, this is the learning rate. It has to be much smaller than 1, as I mentioned earlier. And this is the target error. So it will be set by the user. So now the first step is to calculate the output of the system. So from the previous example, so we will check the first sample. The first sample has 2 features. So the leaving so 2 features. So the first sample. So we have so yes, it will be for x1, so the first sample. So we will have the living area, and the second one will be the number of bedrooms. So living area 100, 135, 180, and so on. So obviously, if we calculate here the first sample, number of bedrooms is 2 for the first sample, and the living area is 135. Using this initialized parameters, so we will get 308. obviously 308 compared to the desired output, so that's the desired output, we'll get some error. So that's the update of the first parameter, and we'll use exactly the same rule to update this, the second and the third parameter. So we have theta 0, theta 1, and theta 2. So this is for the first sample. Then we calculate the output of the difference for every single sample. So from from 1 to n, we have n samples. If the error is still higher than the target error, so obviously we will look through the same steps. So we will again apply the same steps for the second sample. So that's the update for the first sample, and then we will update it for the second sample and so on. So that's the basically the implementation of the gradient descent method. So we had to calculate initialized parameters, calculate the output of the system, compare the output of the system against the target output, and then update parameters. Check the error. If it is still higher than the target output, go back to step 2. Okay, so this is the basically the practical implementation of the gradient descent method. So now once we reach the target error set by the user, then we can test the system. So we can use samples that have not been presented to the system before. So the system will be expected to predict, to estimate output in new situations. Okay, so we will use, so we have training samples, we will use basically testing samples to measure the performance of the trained system. So once the system has been trained, which means parameters have been updated so that the target error is achieved, new data is presented at input, so which means in our example we can have some new living area numbers and number of bedrooms data, and the system should be able to predict the price. Now, the purpose of conducting testing is to make sure the trained system is reliable. So we've got, because if you apply the system, or if you measure the performance of the system on the training data, obviously you will get extremely high accuracy, because that was the data used to train the system. So the system has learned on the training data. But we need to make sure the system is reliable. So we have to use a different set of data. New situations. New situations will be presented to the system and then measure its performance. Okay, so the testing of the system should always rely on new situation, new samples that have not been used to train the system. So yeah, basically that's the gradient descent method used for linear regression. So we've seen different basically the steps implemented to train the system. So we will see in so you'll have 15 minutes break. We come back in a different room, the same building, first floor, 149 or 8. 149. So we will see the linear classification. Basically we use the same principle, but obviously the data will be class labeled. Output data will be class labeled instead of numbers.
Yes, I'll be proactively.